Let floor x denote the greatest integer not exceeding x. Then the integral from 0 to infinity of floor x times e to the negative x dx is equal to one of these quantities. Okay, I actually did a question like this somewhat recently. Well, I shouldn't say like it was quite different, but it involved an integral that had the floor function in it somewhere. So my first instinct here is to just write this as a sum. I mean, this function is piecewise constant over every interval, every subinterval of the real line of length 1, like between the integers. This is a constant. So if I write this integral as a sum of integrals over subintervals, so let's write this k goes from 0 to infinity, an integral from k to k plus 1 of x e to the negative x dx. Now, within any one of these integrals, this is a constant. So I can write it as k times e to the negative x dx. And of course, this k doesn't depend on the variable of integration, so we can take that out in front like this. This integral should be pretty easy to evaluate. So this is e to the negative x with a negative sign, evaluated at k and k plus 1. Which is e to the k minus e to the k plus 1. Oh, I've got some negative signs in here like that. And I should be able to factor something out of here, right? K goes from 0 to infinity of k times e to the negative k 1 minus e inverse, right? I hope I'm not going through the computations too quickly here and making a little mistake, but I think I've got that correct so far. So I have 1 minus e inverse times a sum. K goes from 0 to infinity of k e to the negative k. Okay, so it's an arithmetico-geometric series. I don't remember the formula exactly for this, but I think this is equal to 1 over 1 minus e inverse squared, in which case the answer becomes 1 over 1 minus e inverse. And that's not... is that one of the options? No, did I make a mistake somewhere? I might have to derive quickly what the formula for that thing is. Let me just, before I do that, let me try to see if I can find a mistake in my algebra somewhere, in case that solves the problem. Unless maybe if I complete, so this is 1 over 1 minus 1 over e, 1 over e minus 1 over e, which is e over e minus 1. No, that's still not one of the options we're given. Okay, I'm going to have to take some time to try and derive the formula for this thing. So I think now I'll just, if I take a limit as n goes to infinity at this point, it might be okay. Well, no, maybe I should write this as, this is 1 minus r to the n minus 2 over 1 minus r. And I have to divide this by r minus 1. So let's instead flip the signs of everything and divide by 1 minus r again. Okay, parentheses here. So now s infinity is, so r has to be less than 1. That's gone. That's gone. So I get that, which maybe I can simplify. I'm a little bit surprised to see the negative r squareds combine here. Oh, I have a sign error all over the place. Yeah, just a minute. Let's do this as top minus bottom. Oh man. I don't want to have to fish for where the sign error is, so let's just Sn minus r Sn, top minus bottom, r plus r squared plus r cubed plus rn plus n, r to the n plus 1. No, top minus bottom. Okay, so this makes more sense. I mean, the fact that we have just a standard geometric series here. So if I factor out an r, I get 1 plus r squared, r to the n minus 1 minus n r to the n plus 1. So this is r times 1 minus r to the n over 1 minus r. Okay, so Sn is all this divided by 1 minus r. And so S infinity is r over 1 minus r squared. Okay, and in our case, S infinity, this is E inverse divided by 1 minus E inverse squared. And if I go back to my original problem, so this is where things might be incorrect after here. So we're going to ignore that. So I need 1 minus E inverse times the sum. So I have 1 minus E inverse times E inverse over 1 minus E inverse squared. And now if I simplify things, E inverse divided by E minus 1 over E, that should be 1 over E minus 1. And I think that's one of the options. Yeah, that's option B. Okay, took a bit of a roundabout way of getting there. I mean, my first step, I'm sure was correct. Breaking this integral up into a sum of integrals over subintervals seems like a perfectly reasonable thing to do, given that this function is constant over each of these intervals. The integral itself was fine. It was just, I mean, I did something with an arithmetico-geometric series, I don't know, 2 months ago. And even, you know, I don't have this formula memorized. I don't have that memorized. You know, I haven't used that since high school, so whatever. But the technique to derive it is kind of what the standard thing you would try given something that looks like this. But yeah, I did some of the mental arithmetic incorrectly. Obviously, I mixed up whether I was subtracting the top and the bottom or whatever. So obviously the first time I went through this, there were some mistakes, but got there in the end. And I hope that's correct. If it's not, I'll let you know. Thanks for watching.